Hi, my name is Riku Adachi from the University of Tokyo. Today, I would like to talk about, I'd like to present you the lifelike behavior of an oil droplet in an aqueous surfactant solution, comparative analysis with Tetrahymena, movement and numerical simulation. Life is a self-sustaining chemical system capable of Darwinian evolution. This is a definition by NASA. Definition of life by NASA. So, however, once we're on the same page in ALIFE community, we will not satisfy this definition. So, the open problem of ALIFE, one of the open problem of ALIFE is transition from non-life to life. So, naturally, the question is, what is life and what could be, or what constitutes life? So the initiation or starting point is pillars of life instead of, this in a broader sense, rather using the or standing at the typical definition of life. So, for example, Okay, so our focal point is dissipation or dissipative structure. The foundation of life in a broader sense. So typically you can observe the dissipative structure within the behavior or spontaneous motion, which is observed regardless of non-living and living system. Namely, our self-propelled particle as a non-living matters and also living matters, for example, microorganisms. That exhibited spontaneous movement under the far-flung equilibrium environment. So here is summary in one page. First and foremost, our research focusing on the understanding of the border between non-living and living matter, a non-living and living system, and quantitatively compare these two systems at the same time and find a characteristic exponent that differentiate these two systems. So the things we have done in this presentation is, one, conducting experiment on the single oil droplet. Two, quantitatively analyzing behavioral patterns of non-living and living system. Three, performing numerical simulations of two-dimensional Langevin equation. So this figure shows our result in a simple way. So we just line up our result of the trajectory of oil droplet and Tetrahymena and kinetic energy distribution in one spectrum, depending on one order parameter, that is droplet size. So again, the focal point is autonomous movement, so which is a manifestation of properties of dissipative structure. These videos shows the spontaneous movement of oil droplet and Tetrahymena respectively. So it's quite hard to see, but Tetrahymena is cruising in petri dish, with sufficient nutrition. And on the other hand, we have oil droplet system that's cruising in the petri dish. So, but many researchers have been dedicated to these systems within not only the ALIFE community, but also statistical or outer equilibrium physics, such as active matter physics as well. However, these researches has been conducted independently because they have not shared their motivation to reveal their lifelike behavior, what kind of constitute lifelike behavior is or something. So we just like to integrate these discussion that conducted independently, and it may provide an exponent that characterizes differences between lifelike behavior. Differences between non-living and living matter. So at first glance, you will notice that both systems have a structure that is sensory motor coupling here. Individuals acquire information from the environment and then spontaneous behavior emerges. The internal state fulfill an essential role in generating the motion as observable output. So individuals sense the signals from the external environment and respond to them. So oil droplet and microorganism look seemingly different. However, there are a bunch of similar properties, such as communication with the outside external environment or external environment, and sensing the signal that is from the chemical reaction or something, or sensing the kinetics from the external environment as well, and show the spontaneous complex life-like behavior. So since oil droplet system is strongly coupled to the environment and susceptible to a fluctuation, we can hypothesize that non-living system largely outsource the behavior via communication with their environment, and we can expect the vestige of information acquisition, and we can expect the and processing within some internal states appear in the spontaneous motion of oil droplet motor, non-living matter and living organisms. Thence, we try to extract the underlying dynamics from the lifelike behavior of non-living and living system, depending on statistical analysis and nonlinear dynamical analysis. So here is the method of our experiment here. It's really simple. And an oil droplet that is mixture of ethyl salicylate and paraffin is dropped in the aqueous solution of sodium dodecyl sulfate. It is called SDS. That is typical anionic surfactant solution. And we just recorded the spontaneous motion of an oil droplet that is spontaneous. The oil droplets spontaneously break the symmetry in the petri dish because of the fluctuation of chemical reaction between the external environment and the oil droplet itself, and the kind of emerging behavior of an oil droplet is recorded for 30 minutes or so, and we just extracted the trajectory of oil droplet in this experiment. And for Tetrahymena, confined in a two-dimensional microculture arena and observed under stereo microscope with sufficient resolution. So since it should be easier to understand the experiment setup, here's a video of an oil droplet. Depending on some certain parameters of oil droplet, I mean the volume and volume and composition ratio of droplet of oil droplet is a parameter in this experiment. So depending on these parameters, the oil droplet motion is really different. I mean, in this case, it's moved really kind of complex manner actually. So it's just not only just rotating in some place, but also shows some kind of this kind of straight like motion at the same time. So in the analysis, first of all, we just here we will show some kind of trajectory of oil droplet here, and oil droplet and Tetrahymena for you don't misunderstood. And here these three trajectories show the oil droplet motion of oil droplet respectively. So we just categorize the trajectory of oil droplet depending on not only the geometry of trajectory, but also kind of kinetic energy distribution that will be elaborated later. So we say a circular type of movement and chaotic reciprocating movement of oil droplet, and the bottom shows corresponding velocity. So you will see some kind of fluctuation in the chaotic motion as well. And on the contrary, Tetrahymena shows far more random type of movement. So here shows the kinetic energy distribution and the phase diagram of it. So the definition of kinetic energy distribution is the difference between of x directional and y directional differences of square of differences x directional and y directional differences. So here the top one shows the oil droplet kinetic energy distribution. It's like a Gaussian type of distribution and exponential one. On the contrary, the Tetrahymena shows Maxwell-Boltzmann distribution, and the important thing is the deviation from the ideal Maxwell-Boltzmann distribution. So to understand the underlying dynamics of both system, I mean the Tetrahymena, the underlying or governing dynamics of living system and non-living system should be different. So we just try to extract the dynamics of both systems respectively. So to understand that, we computed embedding dimension. That is, simply speaking, or rough sketch, it is exponent. It is a dimension or complex, the value of complexity of the system as a minimum number of variables necessary to reconstruct in a state space. So for Droplet, this is x-axis shows the embedding dimension for 1 to 15 or 30 minutes. 30 dimensions, and y-axis to the prediction skill. That is correlation between the original data and predicted data. So here shows you will find the optimal embedding dimension when this the improvement of the prediction skill is saturated to some extent. So for Droplet, you will see some kind of 5 or 6 embedding dimension will be saturated in each case. I mean, each line shows the different volume of Droplet. So it shows like 5 or so embedding dimension would be optimal to express the dynamics of Droplet. So that means kind of deterministic type of behavior would be existing in the Droplet system. In the contrary, for Tetrahymena, that shows its kind of fluctuation, and you will not find saturation of prediction skill here. So it is quite difficult to find optimal dimension. That means much more stochastic manner that Tetrahymena has in their dynamical system. So that means that some deterministic dynamical systems are to be underlying the Droplet experimental system. So at the same time, we calculated the largest real-time exponent, LLE here. That is the measure of chaotic behavior, or just it's requisite to be a chaotic system that shows sensitivity to the initial value. When positive, that means exponential growth of 2 different initial value differences. The definition is here. And so for the Droplet, we plotted the largest LLE as a function of volume. It's tend to decrease with the increments of volumes and reaches the minimum when the volume is 20 microliters or so. Contrary, for the Tetrahymena, the LLE of 4 individuals is plotted. The values are almost the border between positive and negative. Thus, we would say that while the Droplet system has a parameter region that exhibits the chaotic system, but Tetrahymena does not. So it proves that underlying dynamics of Droplet is rather deterministic, but for Tetrahymena is not that deterministic, rather, I mean, stochastic or non-deterministic, I would say. So as a reference point, we performed a numerical simulation of a 2-dimensional Langevin equation here. We introduced the external drag forces as a shape of sinusoidal input and reproduced the trajectory and kinetic energy distribution here. As shown in the figures, we successfully reproduced the behavior of Droplet and Tetrahymena respectively. But the thing is, the Tetrahymena shows kind of the experimental data of Tetrahymena shows the deviation from Maxwell-Boltzmann distribution. But in this Langevin equation, it shows kind of analytical solution of Fokker-Planck equation. So that shows kind of deviation. So that means The motion of Tetrahymena is not merely stochastic or random, but it shows some kind of much complex dynamical system would be there. But the current, empirical dynamical systems analysis cannot detect that kind of, much complex or high dimensional chaotic behavior. So finally, here is conclusion. So let me draw a conclusion with a remarkable future outlook. Here we calculated some kind of embedding dimension, the of aqueous surfactant, and the kinetic energy distribution in simultaneously of droplet Tetrahymena. On the reference point, we show the numerical simulation of the Langevin equation. Here, this implies that embedding dimension, the differences of embedding dimension, the underlying dynamics of these non-living system or living system would be different. So at the same time, the kinetic energy distribution also show the different pattern that is characteristic for non-living system or living system. So for the future outlook, we will conduct the experiment of multiple droplets and comparing other living system and quantitatively analyze information flow by measuring the entropy production or some kind of information acquisition from the environment, and the final or ultimate spontaneous movement will be different. Okay, that's all my presentation. Happy to take questions. Thank you.